Okay. I'm recording at this time, just so you know. Um, okay. I'd like to see my command history, but um, okay. All right. This is not entirely proper MATLAB syntax, but you get the idea. And then D2 is Quan. Identity with A plus Quan. Yeah. Okay. Now, the next thing to do was what I covered at the end was red-black ordering. So with n equal 5, this matrix is 25 by 25. So we can matrix call it DRB, and that would be D2, and we'll select, like for instance, the red rows, 1, 2, and we'll hard code 25, then 2, 2, 25, and then same for the columns. Just so we can have both matrices from lexicographic and red-black ordering to work with. Okay. And while you are doing that, well, let me be absolutely sure my commands can be seen by anyone watching. And then cheat a little bit in MATLAB while you're doing that. Okay, so okay. And let me know when you have it ready, all the way down to DRB, or anyone not actually.
So it should be 60, 36, and -9.
I don't really care about so much about the entries, about just that the matrices are made. Yeah. So, if I take a look at the go ahead and look at the entries. I see like 36 and 144.
No, -9.
Wait. Um,
Oh, maybe it's because I went further than what you wrote there and then come back to this one. Maybe that's why.
which matrix are you looking at?
Well, right now this one.
No, no, no. Don't. Pointing is useless. Give me a name.
Oh, D2.
Yes. Okay.
Oh wait, you're doing D2 or DRB?
Well, we need both. Because you have to create D2 to make DRB. Now, DRB and D2 will have the same entries, just in different locations. Because all you're doing is you're reordering the rows and columns. That's not going to change values. Okay, the entries of A should be like minus 36 or 72. The entries of D2 should be either minus 36 or 144. Well, even your A doesn't have the right entries.
No, it was correct. I just. Oh, even A?
Hey, the A supposed to have like minus 36 or 72.
Oh, because it was.
Oh, yeah, it was. Wait, that partly explains it.
So it should be 1.4? And
yeah.
D2 and
Yeah. Okay, that was fine. And now you can go ahead and do the rest. Okay. Now, okay. So here's actually there's a question based on a question that you Ava asked yesterday, just as we were wrapping up, as far as the advantage of red-black ordering for purpose of solving systems. So we're going to take a look at that. What I want you to do next is for both these matrices, D2 and DRB, we'll actually carry out Gaussian elimination so we can look at the factors. So we'll just do like use the LU command, which works for a full or sparse matrix. So like L1U1 would be the LU decomposition of D2, and then same thing for DRB. And then what we'll do is, once you have that, I want to look at the structure of both side by side, the contrast. So, so I'll throw out a command that you may have seen before. I might have used it in some class before, but I want you to be aware of it anyway because it's so convenient. Okay, so then we'll make a figure that has two plots in it, side by side. So we specify a matrix of plots, only one row and two columns. So subplot 1, 2, 1. And what this does is it says make a 1 by 2 matrix of axes and make the first one the current one. And then we can do a spy. We'll look at the upper triangular factors, so U1. And then you go to the other plot, so select the second plot to be the current one, and do a spy of U2. So then we can see the structure of both easily. What's interesting is the subplot command works whether you have the commas or not. It figures out what to do. I guess for backward compatibility, I imagine. Okay. So So when you have it up, let me know, and then we'll discuss. Yes. Now, to refresh our memories, the structure of the overall matrix, so D2 is like a 5-diagonal matrix. That's these really tight tridiagonal bands, and then there's upper bands further away. Whereas DRB had a structure where you had a diagonal matrix in these diagonal blocks, and then you had whatever structure in the off-diagonal blocks, and both matrices are symmetric. Now, yeah, little lowercase l. It's kind of weird how the MATLAB help pages always would use uppercase, let's see, for the commands, but they're supposed to be lowercase. Okay. Everybody else have it up? Okay. So I could. Yeah. Okay. Now, so what happens is, well, okay. First thing to notice before drawing anything, notice the number of non-zeros in the two. Yeah, but you have fewer non-zero entries in the red-black ordering. Now, and I imagine this is something that we were trying later. Here we only have 5 grid points. If we used more grid points, and after we talk about this, we'll actually try that. Imagine the difference would be greater between the two. So that's one thing, but you get somewhat more sparsity. But that's not. But I felt that wasn't really the most interesting thing about this. So L or U1 has a structure. Of course, it's upper triangular. It has to be. But we have 1, 2, 3, 4, 5, 6. 6 bands altogether that are mostly full. Like you get a few zeros up here, like in this upper left corner, but for the most part, these are completely full. Okay, so that's U1. U2 has that going on in the lower 2x2 block, but then the upper block is just a diagonal, and then you have other stuff over here that has a semi-random structure to it. But it's mostly, there's a few bands. There's looks like 4 bands altogether. Yeah, it is kind of zigzaggy in a way. Yeah. Now, imagine performing back substitution. Can you think of any particular advantage to the red-black case? Compared over the first one.
Indices of 4 will be smaller compared to the other one.
Well, not really. Because also you'll have, well, one thing that's about the same is the number of non-zeros for each row is roughly the same. Might be a little bit less, but so.
You already know something about the columns, like when you get up towards the upper half.
Yeah.
You already know, like you know something about the last. Something to do with the, like,
Okay, let's go with that. You started down the path. In terms of which unknowns depend on which other unknowns. Because in this case, each unknown depends on like the 5 or so that come right after it. What do we have in this case in terms of dependence? Yeah, you see, some of the yes, something's very different, but what exactly?
More dependency on zero in contrast to non-zeros in the second one.
That's right. What?
More dependency on non-zero zero elements instead of non-zero. Like in U2 in the bottom block, like you have say the top row of the bottom block, and you are trying to substitute into the one above. You already know the ones that are to the right.
Okay.
Right.
Yes. Okay.
So you only need to find
Keep going.
the ones along the diagonal, or
Yeah. Well, the thing about back substitution, what happens is like this, like one of these xi's would be equal to like your right hand side, whatever that is, minus a sum over certain j of uij xj, where j is strictly greater than I, but it's only the ones that are non-zero, all divided by uii. That's sort of the main back substitution step. So, and so what's happening is, yeah, I think the most important thing that you said was when you get to these guys, you already know these.
yeah, that's what I'm trying to say.
Yeah.
So you only have to solve for.
Well, it's okay. You're almost there. Now, because what happens is in this case, like if I'm up here, for instance, I can't compute this until I know these other ones, and therefore I can't compute. And to compute those, I need the ones right next to it, and so forth. As opposed to this case.
So once you get up to that point, it's going to eliminate like a whole.
Yeah. And what ends up happening is you are allowed to compute these guys independently of each other.
Oh, okay.
Because they all depend on these. So you have to go to the same trouble to produce these unknowns. But once you have them, these are independently, and therefore you can compute them.
Simultaneously?
Yes,
Okay.
in parallel. Simultaneously. So, so that worked out pretty nicely in that case. So that's one benefit is property A structure. Now, if we go back and I'm going to set n equal like I'll just do like 1,000, let's say, and just go through the similar commands. Okay. Create A, and then I compute D2 and DRB. Do careful. Like repeat all the commands, like E equals 1 to N1. Yeah, but I forgot to repeat that one. Oh, okay. Oh, okay. What?
What is n sign?
1,000. Yeah, and then do everything else the same. So you should be able to repeat all those.
Okay, I won't stop running, I think, because it's so big. I probably need a
Oh, yeah, definitely put semicolons on everything.
How do you stop it again?
Control C. Of a,
I had an error in con.
that's weird. What kind of error did it give you?
I don't know.
Oh,
The rate exceeds maximum memory size expected.
oh, you got an out of memory error. Does it say that somewhere?
Creation of arrays greater than this limit may take a long time and cause my life to be extended.
Yeah, I have this.
That's okay.
And it says the same thing, error.
Oh, I forgot to recreate identity at the right size. Okay, so now I have 1,000. Okay, so now if I do, yeah, so D2 and DRB will be 1,000,000 by 1,000,000, but but sparse. So hopefully, okay, but then again, it might depend on your memory situation. Well, I seem to recall from a brief time I owned your computer that the memory was quite good. So.
Yesterday you said something when you were talking about DRB and you were mentioning that property A. You said if N is even, it won't work. What won't work?
Getting red-black ordering, just doing this. The index pattern is more complicated. So, does this say out of memory?
But we have N is 5 and we got red and black, so I'm trying to understand what you mean. N is 5
Oh,
and we
wait.
got red and black that way.
Okay. When N is odd, then you get red. When N is even.
Oh, when N is 1,000.
Yeah.
So now N is 1,000.
Right. Oh, shoot. I need to pick an odd N.
1,001.
Well, apparently I have trouble with 1,000.
Yeah, I'm trying 101 right now.
Okay. Okay. I'll do N equal 999.
I have a question.
Yeah.
For DRB command, if we choose 1,000, then we have to have 10 to the power 6 instead of 25.
Okay. I'll get to that in a moment. Okay. So D2 is DRB. Okay. So instead of 1 to 2, instead of 25, you'd have N squared.
10 to the power 6.
Or you can just literally type N squared, and then it'll work no matter what N is. Okay. All right. So now I have a matrix that is 998,001 by that much. 999. Yeah. Okay. So you need more memory. You're going for KSS. Okay. Now I want to make sure that. Okay. Okay, yeah, still has a similar structure for red black. That's good. Now, if I do the same LU, bless you. Bless you. Although LU is taking a while. All right. So that could be a problem too. So is anyone able to do 1,000 by 1,000?
It is fine.
You got it? Or?
I mean, I got DRB
Okay.
and
Can you check the size
size
of DRB? My Gaussian elimination is still going. That's unfortunate.
is 10 to the power 6 by 10 to the power 6.
You do N equal 1,000 or 999?
1,000.
I goofed earlier. It needs to be odd,
Okay,
or
so
red black
like
won't work that way. So
999
Yeah.
Okay.
Although now I'm wondering if that's practical because even though it was fine computing the matrix, the LU is taking a very long time.
So why it should be off?
Because otherwise this index pattern won't produce a red-black ordering. And I'll talk more about that in a moment. And now it won't let me control C the LU either. Yeah. Okay, so class may have ground to a halt. Okay, well.
Good time for more questions there? I'm just kidding.
Well, okay, so. Wow. Okay, I'm going to kill MATLAB.
That's what I was thinking too.
They work with one-on-one. They not trying 501.
Yeah,
It's
that's
just not doing it.
501.
Okay, yeah, mine just shut down.
Long time for this one.
It's stuck
Yeah.
in this little loop thing.
I don't know.
They
Mine,
just move it to-
mine don't even
The plotting is the one that takes a while. Wait. So your test right there, put it down there, put it down there. Right there. Right click.
Okay, so MATLAB is dead. So now what I'm going to do is I'm going to go back and do n equal 101.
Yeah, that works.
Okay, and so able, and then LU should take a reasonable amount of time, I hope.
Because 100 is not even
Oh, wow.
it has to be out. Wait. Don't ever do that. You're gonna break the computer doing that. You're gonna
Okay, so now I have like a roughly 10,000 by 10,000 matrix. I'm going to do red black. Okay, L. All right, now LU takes is quick. Okay, so now if I do the same old subplot, I did 101 for n. Okay, so now, okay, so when n is equal to 101, so with lexicographic versus red black, I get 103, 0401. And then red black is 537, 949. So it's a little more than half the non-zero entries. And that's for n equal 100. So if we have been able to do n equal 1,000,
Yeah.
then, but because the thing is, here, the first case, it was less, but it wasn't much less. So but as n increases, that ratio improves. So that's one thing that's quite nice. So, okay. Now, before we look at homework questions, so, well, do you have homework questions?
Yeah, probably.
Okay. Well, I want to be what we're pointing about red black ordering before we leave it. So the whole thing about n even versus n odd. So if I do n odd, so I'll do like a 5 by 5. Then if I look at lexicographic, but now I want to do is red, black ordering. Which cells do I take? So red, black, I would take alternating cells on the first row, so 1, 3, 5, then go to the next row and take cells that are like staggered, alternating between the red ones from the previous row, 7, 9, and so what happens is I just end up taking all the odds. And then once I exhausted all those and I got to 25, I go back down and do the, so red, then black. Reds are odd, blacks are even. Now, for the even end case, so let's do a 4 by 4. Well, actually, I can do a 6 by 6. Just make it a little more interesting. So 1, 2, 3, 4, 5, 6. Alright, so my red cells would be, okay, so first it starts out with the odds, 1, 3, 5. But then when we move to the next row, I can't continue with the odds because those odds are situated above the red cells from the previous row. So now I just switch to evens. 8, 10, 12, and then I can go back to odds, 13, 15, 17, and so forth, and until I get to the end. Then when I go back, same thing, 2, 4, 6 for the black cells, and then I have 7, 9, 11, and then 14, 16, 18. So it's a little more complicated index pattern. And you can see there is a pattern to it.
Why do you have to go from 1 through 5 to 8, 10, 12?
Because if I mark the red cells, there has to be this alternation pattern to it, 2 dimensions.
Oh, I see.
Okay. Actually, now here I've assumed that the number of cells in the x and y directions are the same. But in fact, really, whichever is your like your innermost index, like in this case x, it's the number of cells in the x direction that has to be odd to have a simpler index pattern. It doesn't really matter so much how many cells you have in the y direction. You're just going to go all the way to the top. So that's the real determining factor here for simple red-black versus not so simple red-black ordering. Okay, so something that you could figure out like in code to get it right, but it's just feeling lazy. Okay, now. So are there more questions? Okay.
Oh, yeah, okay. So, on 4B, when we're writing a spectral code using a Truncation look at a singular matrix, do we have to do, what, like Gaussian Elimination?
Oh,
Solve the system?
wait a minute, you got a singular matrix?
Did I screw that up?
Well, actually, now I think about it, it says you do have a singular matrix because since if you take the derivative of a constant function, then that would be 0. So perhaps we think about that.
Yeah, because currently what I have, like, on my homework is like, why would you do this to me? So.
Yeah, so that much of a bastard. Well, now that I think about it, you also passed, if you multiply it by a vector representing a linear function, well, actually, the only null space vector would be a constant vector. And unfortunately, your right-hand side is a constant vector. Well, except that this matrix is not symmetric. So, now what happens is when you try to solve a system, it gives you that like as a warning, I guess.
Yeah. It gives me. I think I broke my luck in that one.
Way to go.
Yeah, that one was very good.
I had erased some stuff, so it's not giving me that same warning anymore. Let me try to do the backslash thing.
Okay.
Sorry. I guess I should. It says warning, matrix is singular, close to singular, or badly scaled. Results may be inaccurate. And then, like my matrix U that I'm usually solving for, when I print it, it gives me just the like NaN.
Oh, okay, that's particularly weird because what it should have done is still produced a solution
Okay.
as best it can. Like for instance, if it can't solve it exactly, then it should produce it in like a least square sense.
So there's probably something earlier in my code that I just missed.
It's something honestly I didn't think about is the fact that you're solving this with a singular matrix. And actually, I did think about that for a periodic problem, but for problem 5.
Yeah.
But in that case, you are dealing with a right-hand side that is in the range. So and it helps that that matrix is symmetric. And so it should not be a problem in that case. Wasn't thinking about singularity in this case. Okay, so let's see. This is just plain old backslash.
Yeah.
Okay, try this. This would be another way to get the best, like least square solution. Okay, try. How many points are you using?
400.
Okay. So try U is equal to P inv of whatever you're calling your matrix.
A.
Okay, that's times your B. So that would give you the minimum norm least square solution, similar to what you get if like you use the SVD.
Error using SVD input to SVD must not contain NaN or I and F.
Oh, that means your matrix itself is flawed.
Okay, so I screwed up somehow with my matrix.
Okay. Well, actually, I want to go ahead and take a look in case. Anyone else working on this part?
So, anyway, I'm sure that I somehow, like, cause I was just sitting here and being like, oh, this makes sense to build this matrix, but, like, I'm sure it's not.
Oh, well, yeah, here's one here. When we do this loop, this would be off-cycle entries. So you need to skip in case when I is equal to 0.
Yeah, that's why I just set it down here.
Wait, yeah, so the xi.
And then, yeah, I just did everything is that, and then I did the diagonal case.
What's your index? Okay.
Oh, oops, that needs to be a K. Thank you.
Right.
Let's see. Oh, still doesn't like that. P in whatever.
What does it say?
Same thing.
Okay, so something else is wrong with the matrix.
Do you want to look at the matrix?
Yeah.
Okay, this is D. Oh, that looks a lot different now. This is D after I. That's not A. Like,
But was built using
no, that's built.
Okay. I'm not sure how much was missed by that interruption recording, but I haven't written anything on the board lately, so nothing's been missed there. But yes, in case they do not get recorded, Chebyshev differentiation matrix for problem 4 must be n minus 1 by n minus 1 because you're excluding the boundary Chebyshev points. For problem 5a, solution exists only if f satisfies a condition. So u is periodic to all derivatives. So all those derivatives are periodic also. So that means that u can be written as a Fourier series, but use a real form of a Fourier series that has a combination of sines and cosines. Okay. Now, and the thing is, we have this A0, which is in there because cosine, we have terms of cosine kx for k equals 0, 1, 2, and so forth, because cosine of 0 is 1. For sine, we only have for k equals 1 on up, because sine of 0 is 0. So my hint for this is to examine minus uxx. And what form does it have? And therefore, what does that say about, because this has to equal f. So if you look at the second derivative, you can get an idea of what kind of function f can be, or what it should not be, and still have a solution. Okay, so take a look at that, and hopefully that will put you on the right path.
Okay, thank you.
Okay. All right, let's break, and then so is that something maybe we could look at later, or
Yeah, that's fine.
okay?
I see you.
Oh, that's true. Yeah. All right, so I'll cover stuff. All right. The last thing I talked about was red-black ordering. We did all that. Okay. So looking at apparently these notes switch from, okay, be careful with my minus signs here. Excuse me, dang it. Okay, so 2D Poisson's equation. So minus Laplacian of u is equal to f. Now, we have, so what the matrix that we've built using a center difference in one dimension that we use a product to extend to 2 dimensions is a 5-point stencil. And it's called 5-point because we approximate the PDE at each point ij using its immediate neighbors to the left and right. So I minus 1j and I plus 1j, and also in y direction. So I j minus 1 and I j plus 1. So what we could do is by Taylor expansion, we could figure out the local truncation error with a stencil. So we did something like this already in one dimension when you did it in the homework as well. And what we get is I'm going to use this notation, Laplacian, with a subscript of 5. And this is the 5-point stencil approximation of Laplacian. Turns out to be equal to the exact Laplacian term, so h squared over 12 times fourth derivatives with respect to x and y of u. Excuse me. And then there are additional error terms of the order h to the fourth. Assuming you're using the same spacing h for both the x and y directions. So delta x equals delta y equals h. Okay, so second order accurate like you expect. But now suppose we use a 9-point stencil where we use the Taylor expansions of u at involving all, not just the 4 direct neighbors, but the 4 corner points. Okay, that dot's a little off because of where I wrote, but you get the idea. This is, believe it or not, supposed to be square. So we use Taylor expansions of all these guys. So I minus 1 to I plus 1, j minus 1 and j plus 1, all 9 possible combinations of those. And the idea is we use the Taylor expansions at these other points thrown in the mix to cancel out as many error terms as we can. And what we get in that case is the 9-point Laplacian is equal to the exact Laplacian plus, and our first error term is, okay, I'm sorry, I made an incorrect statement earlier. Because on the one hand, it is still, the leading error term is still second order. But what we get is, okay, so similar error terms before, uxxx, but we have a cross term, 2uxxyy plus uyyyy, and then something is order h to the 4. But there's a way that we can express this error term that we could not do with the previous one, because this is actually the Laplacian of the Laplacian of u. But we know what the Laplacian, the exact Laplacian of u is supposed to be. It's supposed to be minus f. So now we can take that into account. So we have exact Laplacian of u minus, and this is where I have a typo to know, so I have plus there. Okay. So now what that means is I can do, I can cancel out this error term because this is something I can actually compute. That's the difference, because since I don't know the exact solution, I can't compute that exactly. I can compute this because I know what f is. And I can take its Laplacian, at least to a second order approximation. So any error that I have in computing the Laplacian of f is of order greater than h squared. So I can still cancel out the leading part of this error term and get greater than second order accuracy. So what we can do is solve. So using the 9-point stencil, I will solve this modified equation. Laplacian of u is equal, minus Laplacian of u is equal to f minus square root of 12 Laplacian squared f. Actually, in the notes it has a minus here, but this does not jive with what was on the homework. It's at a plus. So I'm going to go out on a limb and put a plus. And see if what I do next in the notes works. Because then my local truncation error in that case, because now I'm going to take this and approximate this, still using the 9-point Laplacian. So my local truncation error is when I substitute in the exact solution into this equation here. So, this is a PDE I want to solve. The approximation I'm going to use to try to solve it is minus 9-point Laplacian with this modified right-hand side. And now, since I know what this is, I'm going to have local truncation error is the Taylor expansion of the 9-point Laplacian, which is up here. So minus Laplacian squared of u minus h squared over 12 Laplacian squared of f plus order h to the fourth. Okay, so all that, and then I subtract this, because for local truncation error, I take my right-hand side, move it to the other side. So I get minus f minus h squared over 12 Laplacian squared of f. Okay. All right, good. Now, Laplacian squared of, Laplacian squared, gradient squared. Laplacian of u is equal to minus f. So I have minus of minus f, which is a plus f, cancels with this minus f. So these cancel each other out. And then I have plus h squared over 12 Laplacian of f, and minus h squared over 12 Laplacian of f. So those cancel out too. Okay, and what's left is order h to the fourth. So this is the same thing you observed in problem 2C of homework 1. When you do this deferred correction, that's what this is. Okay. Then so simple modification, just changing a right-hand side, you don't even change the matrix, gives you fourth order accuracy instead of second. Any questions about how that played out? And you kind of observed a phenomenon already in 1 dimension. And now we see it works in 2 dimensions also, but only the 9-point stencil, not the 5-point stencil. We couldn't have done it this way using that method. And now I'm remembering way back about 20 years ago or so when I was at a conference at Stanford, and this guy was giving me a talk about deferred correction. So he thought he'd be funny at the beginning. He said, this talk is about deferred correction, so if there are any mistakes, I'll fix them later. And actually, you guys laughed more than the audience did. So, okay. Maybe it's my biting sarcasm that helped. It's all in the delivery, I guess. Okay. So that's one thing to think about is, can you gain an advantage by choosing a better right-hand side? Now, the rest of what I have in this chapter, which I will barely get to scratch the surface today, but I can get into more tomorrow, depending on whether or not any of our homework questions. Haley?
I'm doing it. Come on.
What? I know.
I'm doing it.
Good point. All right, so I'll save my ire for the rest of you. So how to solve the system that you get after spatial discretization, whether it's finite difference or spectral or whatever, you have some matrix, some right-hand side, and then your unknowns that is your solution at whatever grid points you're using, whether it's a uniform grid or equal spacing or Chebyshev points or anything else.
Those are all H's, right?
Yes, those are all the subscripts are H's. So this reflects like the approximation that we get after discretizing. Now, if it's spectral, generally the FFT is the best way to go. Even if it's Chebyshev, because you can use the FFT because of the close relationship between the Chebyshev polynomials and cosines. Okay, so if it's finite difference or finite element or finite volume, which is good for advection equations especially. We'll actually use it for Poisson's equation also. When you have like discontinuous coefficients, it's really good for that. Then there are several approaches you can choose that come from, well, 610. So direct methods. So Gaussian elimination. Which leads to PA equals LU factorization. What are some other factorizations? Some other direct methods that we can use that would result in different factorizations. Yeah. LDLT or Cholesky. Now these are limited in their use. Like LDLT requires the matrix to be symmetric. Cholesky requires to be symmetric, positive, definite. But they're out there and they're faster. You don't want to just say Gaussian elimination. Okay, so that's one class of methods.
I have a question.
Yeah.
It might not be related, but what do we use SOR for in 16?
Yeah, coming up next, actually. Stationary iterative methods. Which are called that because they use some form of fixed point iteration. So they all can be viewed that. Okay. So these methods that we saw in 610, what we didn't talk about in 610 was that these are essential ingredient in multi-grid methods that apply these iterative methods on different levels of grids, and that's because of how they eliminate error. So we're taking advantage of certain properties of these methods to enhance accuracy and speed of convergence even more. And that'll be the subject of the third and final homework. And then we have non-stationary iterative methods, which are also known as Krylov subspace methods. So iterative methods of a different sort. What are some of those? Yeah, conjugate gradient if matrix is symmetric, positive, definite. That doesn't fall in that category.
Yeah.
That is a class all its own. Well, kind of, yeah. It's a bad one, but what are the ones that are used for more general matrices? Because that's for symmetric, positive, definite. SymLQ. Yeah, that's for symmetric, indefinite systems. And then there's GMRes, BiCG, MinRes, which is also for symmetric, and so on. Many such methods.
So how about those methods of which class?
Of these? No.
GMRES.
Oh, no, yeah, but these are all Krylov subspace methods.
Right, but I mean, I'm wondering how she knows. Was it like a special class? Research. Okay.
Yeah. Well, also when you took 610, I spent more time on those kind of methods. I kind of had to skip them.
Yeah.
For you guys, but they're in and out stuff. But yeah, research would have done it too. Okay. So really, what's ahead is to spend some time on each of these categories, and even though a lot of it is going to be review, what I found in preparing the notes was that because of the different source and a different perspective on these methods, especially the stationary ones.
So, excuse me, KSS, as Haley said, does that fall in this category? Non-stationary?
Well, the thing about this is all of these methods can be used for a general linear system, and KSS really is really for matrix function vector products. So it goes beyond the inverse. Also, it's intended for very narrow class, like based on differential operators. And the other thing is, while in its most commonly used form, it's more easily comparable to time-stepping methods, which that'll be the last topic of the course. Yeah, it's just weird. That's the problem. It's difficult to classify.
Okay, so excuse me, one more question came to my mind. Seems that this, well, I'm not sure, I cannot distinguish kernel subspace from KSS. I would like to know if this kernel subspace falls to the category of time-stepping methods also.
Well, Creel subspace methods, they can be used for time stepping. However, often used is to just go compute a solution in one shot, like from 0 to final time, except for stiff problems, it's not practical to do so because the Creel subspace gets so large. Because Creel subspace is really any method that uses subspaces starting with like an initial vector and then multiplying by a matrix and multiplying by the matrix again. So B, AB, A squared B, A cubed B, and so on. Or it may not be A, it could be like A plus a shift inverse, repeated multiple. That's rational Krylov, which actually is being used in our paper. So,
The current one?
yeah, the Krylov projection.
Yeah.
Yeah, because I tried regular Krylov projection and it was awful. So I thought, well, maybe rational Krylov would be some good competition for our methods, and it was. But still lost though. Okay, so during the last few minutes, I'll say what I can about direct methods. Okay, so the idea is for a generic system, AX equals B, we, for general case, we perform Gaussian elimination with pivoting, so it's for instance partial pivoting, to get this factorization where P is a permutation matrix multiplying on the left. It just rearranges the rows of A so that Gaussian elimination is possible. L is a lower triangular matrix, and U is an upper triangular matrix. And then, so this is for the general case. And the expense is pretty bad. 2/3 n cubed floating point operations. But we're dealing with matrices normally where that are very sparse, like like a tridiagonal matrix. In that case, it's a lot cheaper. So that helps. So order n, if A is a banded matrix with a small bandwidth. Okay, and then so if it's symmetric positive definite, you can use Cholesky. A is equal to LL transpose. Well, I'm going to call it G because it's not the same L as in LU. Or LD, LT. In this case, that L really is the same as this L if no pivoting is used. One nice thing about symmetric positive definites, you never have to pivot. I mean, you could if you really wanted to, but it's provable that it's never necessary. You don't have to pivot if all the leading principal minors are non-zero, and for SPD matrix are always strictly positive. That was weird.
Just the wind and the blanks on the other side.
Okay.
We had to shut the windows in here because that one was going crazy.
Oh, okay. Actually, it's probably my outer room. Or the other classroom. Okay, great. This takes half of a floating point operation to Gaussian elimination. So you really want to use it for that situation. Okay. And in MATLAB, you use backslash operator, and generally if I would perform Gaussian elimination pivoting, I I'm not sure. I'd have to look this up. If it knows that the matrix is symmetric, positive, definite for any reason, or if it bothers checking, because it's not easy to check. If it actually decides, okay, to do Cholesky instead. I don't know if backslash is that smart, but if it's not, or you can use the functions LU to explicitly compute the LU factorization, or Chol to get the Cholesky factor. So most functions can help you do that. Like if you get the LU factors, you can use backslash with L and U, and it'll see, oh, if matrix is upper triangular or lower triangular, it won't bother to do elimination. It'll do the right kind of substitution. So it does have that kind of intelligence in it. Okay. Let's see. Actually, this next section I already talked about that one of the drawbacks of using these direct methods, if A is sparse, you get what's called fill-in. So you get new non-zero entries. So your LU factors might be less sparse than the original, and it makes the solution process more expensive. And this is why the SPY command is handy. You can use it to examine the sparsity of your matrix. Okay, and this is why red-black ordering can be a good idea for certain matrices. But there's actually some MATLAB functions that can help you with a more general matrix. That help you reduce fill-in. All right, so one matrix is called COLAMD. And I can't believe I forgot to write down what that stands for. So, actually, I'll write out the interface. So, it returns a permutation matrix. Okay.
Approximate minimum degree
Yeah. Yeah, I knew that M was minimum. I forgot what the rest of it was. So the idea is to use the permutation that it gives you to permute the columns of A. So you perform permutation first, and then solve your system, and then you can undo a permutation to put the unknowns back in the original order after you solve. So that's for general matrices. And then the second function for symmetric matrices, SimAMD, so symmetric approximate minimum degree, rows and columns. So using these permutations appropriately for each case reduces the amount of fill-in that you would get due to Gaussian elimination and pivoting. Okay, pivoting especially can be really bad for sparsity, like what it could do to a banded matrix is especially awful. But pivoting is needed for a general matrix. Okay, well, that could be something that might be interesting. If I come up with a good test case, I think I might know of one we could play around with. And I'm actually at the end of a subsection. So this is a good stopping point. So I'll continue with direct methods tomorrow.